Welcome to Scientific Serenity. Tonight, we close our eyes not just to rest, but to travel. We are boarding a vessel that sails not through space, but through time and understanding. Our destination is not a place, but a perspective. We are going back to see the sky not as we know it, but as our ancestors saw it, a place of wandering lights, divine omens, and profound mystery. This is the first chapter in the story of how we were wrong, and how that wrongness led us to the stunning truth, the story of our solar system. Picture a world without electric light, a world where night, true night, is a vast, black canvas stretching from horizon to horizon. The only illumination comes from the cool, distant glow of the moon, and the piercing, steady burn of countless stars. But among those stars, a handful behave strangely. They don't stay fixed. They wander. The ancient Greeks called them planets, wanderers. For thousands of years, across countless cultures, these wanderers were not worlds. They were points of light, deities, portents. To the Babylonians, they were gods writing fate in the sky. To the Maya, they were celestial beings influencing time and agriculture. In ancient China, they were celestial officials and a cosmic bureaucracy. They were part of the heavens, a realm considered perfect, unchanging, and fundamentally different from the flawed, changeable earth below. This belief crystallized into a powerful and elegant system, the geocentric model, championed by the Greek philosopher Claudius Ptolemy in the 2nd century AD. In this model, Earth sat, immobile and grand, at the very center of the universe. Around it, in perfect concentric circles, revolved the moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn. Beyond them lay the sphere of the fixed stars. This was not just science. It was theology, philosophy, and common sense all woven together. You could feel the stable earth beneath your feet. You could see the sun and planets moving across the dome of the sky. The model explained the basic motions. It placed humanity, God's greatest creation, at the literal center of creation. It was beautiful, logical, and completely, utterly wrong. But even within this era, the seeds of true discovery were being planted. The wanderers posed a problem. If they moved in simple, perfect circles around Earth, their observed paths should be straightforward. Yet they weren't. Planets like Mars would slow down, stop, reverse course in a retrograde loop, then resume their forward motion. To save the geocentric model, Ptolemy introduced a brilliant, if convoluted, fix epicycles. A planet moved in a small circle, an epicycle, whose center itself moved along a larger circle, the deferent around Earth. It was a cosmic dance of circles upon circles, a mathematical contrivance to force the observations to fit the theory. The system worked mathematically. It could predict planetary positions with reasonable accuracy for its time, but it was a house of cards, growing more rickety with each new, precise observation. For over a millennium, this was the universe. A Earth-centered cosmos of crystalline spheres and complex epicyclic dances. It was a universe of profound meaning, where every celestial movement was a divine message. To look up was to look into the mind of God, but it was also a prison for thought. To question Earth's central, privileged place was not just scientific heresy. It was theological and philosophical rebellion. The first major crack in this prison appeared not with a telescope, but with a mind. In the early 16th century, a Polish mathematician and canon named Nicholas Copernicus, studying ancient texts and his own calculations, dared to imagine a different layout. What if the sun, not the earth, was at the center? What if the earth itself was just another wanderer, spinning on its axis and orbiting the sun? He published his theory in 1543 in the book De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres. The heliocentric model was born. The Copernican model was revolutionary, but it was also clunky. To make it match observations, Copernicus still relied on epicycles, though fewer than Ptolemy. His sun-centered orbits were still perfect circles, and the model offered no physical proof. It was a mathematical hypothesis that simply made the cosmos simpler. It removed Earth from the center and demoted it to a mere planet. This was a shattering psychological blow, but not yet a proven fact. The true solar system was still hidden, waiting for a tool that could bring the distant points of light into focus, and for a man brave enough to point that tool at the sky and believe his own eyes. That tool was the telescope, and that man was Galileo Galilei. In 1609, Galileo, hearing of a Dutch invention that made distant objects appear closer, built his own improved version. He turned it to the heavens. What he saw did not just support Copernicus. It exploded the ancient worldview. The moon was not a perfect, smooth sphere. It was scarred with mountains and pocked with craters, a world like Earth. The sun had blemishes, sunspots, that moved, proving it rotated on its axis. It was not a perfect, immutable celestial body. But his most stunning discoveries came when he looked at the wanderers. He saw Venus go through phases, just like the moon, from crescent to full. This could only happen if Venus was orbiting the sun, not the earth. Ptolemy's model was impossible. Then he turned to Jupiter. He saw 4 tiny points of light, arranged in a line, orbiting the giant planet. They were moons. Jupiter had its own satellites. This proved that not everything in the cosmos revolved around Earth. Earth was not the sole center of motion. Galileo published these findings in 1610 in Sidereus Nuncius, the Starry Messenger. The evidence was visual, undeniable to anyone who looked through the telescope. The geocentric universe was shattered. We were not the center. We were a planet orbiting a star, in a cosmos far stranger and more magnificent than anyone had dreamed. Yet, the true nature of our solar system, its scale, its composition, the full roster of its worlds, remained a mystery. The telescope had shown that the planets were not mere lights, But worlds? But what kind of worlds? Were they solid like Earth? Gaseous? Could they harbor life? How far away were they? The journey from wandering light to world was complete. The journey to understand those worlds was just beginning, and it would require not just better telescopes, but new physics to explain why those worlds moved as they did. A man born the year Galileo died would provide that. His name was Isaac Newton. But that is a story for another night. For now, as you drift towards sleep, imagine the shock, the awe, the fear, and the exhilarating freedom of those first moments of true discovery. Picture Galileo, alone in the Italian night, peering through his lens, watching the moons of Jupiter dance, knowing he was seeing something no human had ever seen before. He was looking at the first hard evidence of a new reality. We began this chapter with a sky full of mysterious, divine lights. We end it with the dawning realization that those lights are places, other places. The journey from myth to map had taken its first, irreversible step. The telescope had shattered the old celestial spheres, but it left a profound question hanging in the void. What held the new universe together? If Earth was not the anchored center, and planets were not embedded in crystalline shells, why did they orbit the sun? What invisible hand guided their paths? The answer would come not from looking up, but from looking down, at a falling apple, at the swing of a pendulum, at the fundamental mathematics of motion. It would come from Isaac Newton. Newton's genius, published in his Principia Mathematica in 1687, gave the solar system its gravity. Literally, he proposed that every object in the universe attracts every other object with a force proportional to its mass and inversely proportional to the square of the distance between them. This universal law of gravitation was the glue. It explained why the planets moved in ellipses, as Johannes Kepler had meticulously calculated from observational data, around the more massive Sunday. It explained tides, the trajectory of cannonballs, and the fall of an apple. For the first time, the cosmos was not just described. It was explained by a single, elegant, universal force. The planets were no longer pushed by angels or riding on spheres. They were falling perpetually around the sun, held in a perfect balance between inertia and gravity. With Newton's physics as their guide, astronomers of the 17th and 18th centuries began to measure the solar system with new precision. They used transits of Venus across the sun to calculate the astronomical unit, the distance from Earth to the sun. The scale of the system began to dawn on them, vast, empty, and breathtakingly large. The planets were not just points of light, nor were they small disks in a telescope. They were distant worlds separated by millions of miles of nothingness. But the telescope, now coupled with Newtonian mechanics, kept revealing surprises. In 1781, the German-born British astronomer William Herschel, while conducting a systematic survey of the sky, found an object that didn't look like a star. It appeared as a small, fuzzy disk. At first, he thought it was a comet, but its path was nearly circular, and it lacked a tail. Calculations soon revealed the truth. Herschel had discovered a new planet, the first to be found in recorded history. He named it Georgium Sidus, George's star, after his patron, King George III. The international astronomical community later settled on Uranus, after the Greek god of the sky. The discovery of Uranus was a monumental shock. For millennia, the solar system had consisted of 6 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, plus Earth's moon. That was the natural, complete order. Uranus broke that order. It immediately doubled the known size of the planetary system. It proved that the solar system was not a finished, known entity. It contained unknown, major worlds waiting to be found. The map was incomplete, but Uranus itself soon became a mystery. Its observed orbit didn't quite match the orbit predicted by Newton's laws, even when accounting for the gravitational tugs of Jupiter and Saturn. It was straying off course. There were 2 possibilities. Either Newton's sacred law of gravity was wrong at such great distances, or there was another, unseen mass tugging on Uranus, an 8th planet. The hunt for this phantom planet became one of the greatest detective stories in science. 2 mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently tackled the problem. Using only Newtonian mechanics and the irregularities in Uranus's orbit, they calculated where this unseen planet should be. Le Verrier sent his predictions to the Berlin Observatory. On the night of September 23, 1846, astronomer Johann Gottfried Galle pointed his telescope to the predicted coordinates. Within 1 degree of where Le Verrier said it would be, they found a faint, blue-green disk. Neptune. This was a triumph of human intellect. A planet had been discovered with mathematics before it was seen with a telescope. It was the ultimate validation of Newton's universe. The solar system was not only discoverable, it was predictable. The law of gravity ruled supreme from Mercury to Neptune. Yet, even as the 8-planet system seemed complete, the inner planets, our closest neighbors, held their own, more intimate secrets. While the outer solar system was being mapped by mathematics, the surfaces of Mars and Venus were being misread by hopeful eyes. In 1877, Italian astronomer Giovanni Schiaparelli observed Mars during a favorable opposition and reported seeing canali, Italian 4 channels. The word was mistranslated into English as canals, implying artificial construction. This sparked a frenzy of speculation, championed by the wealthy American astronomer Percival Lowell, who built an observatory in Flagstaff, Arizona, primarily to study Mars. Lowell mapped hundreds of straight lines crisscrossing the Martian globe, which he believed were irrigation canals built by a dying, intelligent civilization to transport water from polar ice caps. The public and scientific imagination was captured. For decades, the idea of inhabited, engineered Mars was a powerful myth. At the same time, Venus, shrouded in thick, perpetual clouds, was seen as a humid, swampy, prehistoric jungle world, a sister to Earth, perhaps teeming with life. It was our twin, hidden under a global veil. These were not just scientific hypotheses. They were mirrors. We projected our hopes, our fears, and our own image onto these blank canvases. Mars became a dying civilization, a warning. Venus became a primordial Eden, a hope. We had moved from seeing planets as gods to seeing them as worlds, and now we were populating them with our own stories. The true nature of these worlds, the frozen, desert reality of Mars and the hellish, crushing greenhouse of Venus, remained locked away, waiting for technologies that could pierce the clouds and see the surface. We stand now, at the end of this second chapter, at the turn of the 20th century. The solar system has 8 major planets, discovered through a combination of accident, Uranus, and sublime calculation, Neptune. We have a physical law that explains their dance, but we are still profoundly wrong about the details. We imagine canals on Mars and jungles on Venus. We have no concept of asteroids as a belt, of the Kuiper belt, of dwarf planets. Pluto is unknown. The Sun's family seems nearly complete, but it is on the verge of another, even greater expansion and correction. The stage is set for the modern era, for the tools that would finally show us these worlds as they truly are, and in doing so, humble us once again. The 20th century did not simply refine our view of the solar system. It shattered and rebuilt it. The catalyst was not just bigger telescopes, but new ways of seeing, radar, spacecraft, and digital sensors that extended human perception across millions of miles of vacuum. We stopped being passive observers and became explorers. And with exploration came surprise, humility, and awe. Our first great correction concerned our closest neighbors, Mars and Venus. The romantic myths of the 19th century crumbled under the cold gaze of science. In the 1960s, Earth-based radar astronomy pierced the thick clouds of Venus. The signals that bounced back told a shocking story. The surface of Venus was not a swampy jungle, but a scorching Hell's Cape with temperatures hot enough to melt lead, crushed under an atmosphere 90 times thicker than Earth's. The first successful lander, the Soviet Venera 7 in 1970, survived for 23 minutes on the surface, sending back data that confirmed a literal pressure cooker environment. Venus was not our twin. It was a terrifying lesson in runaway greenhouse effect. Mars's myth died more slowly, but just as definitively. In 1965, NASA's Mariner 4 flew by the red planet and took 21 grainy, close-up photographs. Scientists and the public eagerly awaited images of canals, oases, or any sign of Lowell civilization. What they saw was a barren, cratered, moon-like landscape. No canals, no cities, no water. It was a cold, desert world. Later missions, like Mariner 9, 1971, which became the first spacecraft to orbit another planet, revealed a more complex Mars, with vast canyons, giant volcanoes, and dried-up riverbeds, proof of a watery past, but not a present civilization. The canals were an optical illusion, a trick of the eye connecting distant craters and ridges under poor atmospheric seeing. Our hopeful projection had been just that, a projection. While we were correcting our view of the inner planets, we were discovering entirely new categories of objects in the solar system. The asteroid belt, once hypothesized as a single shattered planet between Mars and Jupiter, was revealed to be a vast swarm of rocky debris, a failed planet, shaped by Jupiter's immense gravity. Then came the revelations from the outer giants. The Voyager missions, Voyager 1 and 2, launched in 1977, were humanity's grand tour. They transformed the gas giants from fuzzy, colored disks into dynamic, complex worlds. Voyager revealed Jupiter's great red spot as a colossal, centuries-old storm, its moon Io as the most volcanically active body in the solar system, painted in yellows and reds by sulfur, Europa with its cracked, icy shell hinting at a subsurface ocean, Saturn's rings in staggering detail, thousands of ringlets, braids, and spokes made of ice particles, its moon Titan, shrouded in a thick, orange atmosphere, a world with lakes of liquid methane. Uranus and Neptune not as serene, blue-green marbles, but as dynamic ice giants with tilted magnetic fields, fierce winds, and strange moons like Neptune's Triton, with geysers of nitrogen ice erupting under a faint sun. Each flyby delivered the same message. Every world is unique. Every moon is a world. The solar system was not a simple set of planets orbiting the sun. It was a sprawling, diverse, and violently active family of worlds. But the greatest paradigm shift was yet to come, lurking in the darkness beyond Neptune. Since its discovery in 1930, Pluto had held the title of the ninth planet, but it was an oddball, small, icy, with a tilted, elliptical orbit that sometimes brought it inside Neptune's path. As telescopes improved in the 1990s, astronomers began to find other objects in similar, distant orbits. They were part of the Kuiper Belt, a vast reservoir of icy bodies predicted decades earlier. Then, in 2005, a team led by Mike Brown at Caltech discovered Eris. It was initially thought to be larger than Pluto. This triggered a crisis. If Pluto was a planet, then surely Eris was too. And what about the other large Kuiper Belt objects like Makemake and Haumea? Were we about to have 50, 100 planets? The International Astronomical Union (IU) was forced to make a historic decision. In 2006, they voted on a new definition of a planet. To be a planet, a body must 1. Orbit the Sun, 2. Be massive enough to be rounded by its own gravity, and 3. Have cleared its orbital neighborhood of other debris. Pluto failed condition 3. It shares its orbital zone with thousands of other Kuiper Belt objects. It was reclassified as a dwarf planet. The public reaction was one of surprising grief and outrage. People felt a loss. A piece of their childhood cosmos had been taken away. But science had not demoted Pluto. It had promoted our understanding. Pluto was not the lonely ninth planet at the edge of nothing. It was the king of a vast, new region, the Kuiper Belt, a region that contains perhaps hundreds of dwarf planets and tells the story of the solar system's ancient formation. The final act of this revelation came in 2015, when NASA's New Horizons spacecraft, launched in 2006, flew by Pluto. It sent back images that stunned the world. Pluto was not a dead, cratered ice ball. It was a vibrant, complex world with towering mountains of water ice, vast plains of frozen nitrogen, glaciers, and a hazy, blue atmosphere. It had a huge, heart-shaped glacier named Tambarigio. It had moons, including Charon, so large they orbit a common center of gravity, forming a binary system. Pluto was every bit a world, just not a planet by the IU's new taxonomic definition. The mission underscored a profound truth. Labels are human inventions. The wonder is inherent in the object itself. So, what is the true solar system we have discovered? It is this: a dynamic, connected gravitational dance governed by laws we understand. A diverse family of worlds, rocky planets, gas giants, ice giants, dwarf planets, moons that could harbor oceans, rings of ice and dust, vast regions, the asteroid belt, the Kuiper belt, and even farther, the hypothetical Oort cloud, a spherical shell of icy objects from which long-period comets originate. A system still full of mysteries, the true nature of Venus's past, the potential for life in the subsurface oceans of Europa or Enceladus, the composition of distant dwarf planets. We began with 7 wandering lights on crystal spheres. We end with a cosmic archipelago of stunning complexity, a system that has continually expanded and redefined itself with every new tool and every brave question. We were wrong about the center, wrong about the number of planets, wrong about the surfaces of Mars and Venus, wrong about the edge, and in being wrong, we found something infinitely more interesting. As you drift to sleep tonight, let this thought comfort you. Our greatest discoveries have not come from being right, but from having the courage to be proven wrong and the curiosity to look again. The true solar system is not a static picture in a textbook. It is a story still being written, of light becoming worlds and myths becoming maps. And you are part of the species that is writing it. Tonight, we leave the inner, rocky realms of the solar system and venture into the domain of giants. Our journey takes us to a scale that dwarfs human imagination, to worlds so vast they could swallow every other planet whole, and to moons that are worlds in their own right. This is the story of the Jovian Revolution, the moment we realized that the solar system is not centered on the sun alone, but contains other, miniature solar systems within it, each with its own dramas, mysteries, and breathtaking beauty. Our story begins, as so many in astronomy do, with Galileo Galilei and his Achial, his spyglass. In January 1610, Galileo turned his newly improved telescope toward the bright planet Jupiter. What he saw over the next few nights would change everything. Jupiter was not alone. It was attended by 4 small, star-like points, arranged in a straight line on either side of the planet. Night after night, he tracked them. They moved, but they did not move like background stars. They moved with Jupiter, and crucially, they changed their positions relative to Jupiter. On some nights, all 4 were on one side. On others, some were hidden behind the planet's disk or passing in front of it. There was only one conclusion. These 4 stars were orbiting Jupiter. The implications were earth-shattering. Catholic doctrine, following Aristotle and Ptolemy, held that all celestial bodies orbited the Earth. Here was clear, visual proof that at least 4 bodies did not. Earth was not the sole center of all motion in the universe. Galileo had discovered the first known satellites of another planet. He named them the Medicean stars after his patrons, but we know them today as the Galilean moons, Io, Europa, Ganymede, and Callisto. In one observational stroke, Jupiter was transformed from a bright wandering point of light into a planetary system, a central body with its own orbiting family. The cosmos had just become exponentially larger and more complex. For centuries after Galileo, Jupiter and Saturn remained little more than fuzzy disks. Even in improving telescopes, astronomers could track their great spots and banded clouds and marvel at Saturn's enigmatic ears. Its rings, which were misidentified as handles or moons until Christian Huygens, in 1655, correctly described them as a thin, flat ring, nowhere touching, inclined to the ecliptic. Huygens also discovered Saturn's largest moon, Titan. A few decades later, Giovanni Cassini identified a gap in the rings, the Cassini division, and discovered 4 more moons, Iapetus, Rhea, Tethys, and Dione. But what were these giant planets? Were they solid like Earth, but just immensely larger? Were they gaseous? The prevailing theory into the 20th century was the gas giant hypothesis, but it remained just that, a hypothesis. Their composition, internal structure, and the true nature of their spectacular atmospheres were subjects of pure speculation. They were majestic, but remote and enigmatic. The first major leap in understanding came not from optics, but from radio. In 1955, astronomers Bernard Burke and Kenneth Franklin detected intense bursts of radio noise coming from Jupiter. This was the planet's magnetosphere, a vast, invisible bubble of magnetic influence, trillions of times larger than Earth's, interacting violently with the solar wind. Jupiter was not just a big ball of gas. It was a magnetic powerhouse. This hinted at a rapidly spinning, metallic interior, a dynamo effect generating a field of unimaginable strength. Then came the space age. The first robot emissaries to the giants were the Pioneer 10 and 11 probes, launched in 1972 and 1973. Their mission was a brave pathfinding journey into the unknown. They were the first human-made objects to traverse the asteroid belt and fly by Jupiter. Pioneer 10 sent back the first close-up images of the giant in December 1973. The pictures were grainy, but revolutionary. They showed the banded cloud tops in detail, the Great Red Spot as a colossal atmospheric vortex. They measured the intense radiation belts, so powerful they threatened to fry the probe's electronics. Pioneer 11 went on to use Jupiter's gravity to slingshot itself toward Saturn, giving humanity its first fleeting close-up of the ringed planet in 1979. But the pioneers were just the scouts. The real revelation came with the Voyager missions. Voyager 1 and 2, launched in 1977, were equipped with far superior cameras and instruments. Their grand tour of the outer planets was a gamble of celestial mechanics. Once in 176 years alignment that allowed a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune using gravity assists. When Voyager 1 reached Jupiter in March 1979, it didn't just send back better pictures. It sent back discoveries. The Jovian system exploded with activity no one had predicted. Io, the innermost Galilean moon, was a cosmic shock. Instead of a dead, cratered world, it was a psychedelic canvas of oranges, yellows, and reds. Voyager's navigation engineer, Linda Morabito, spotted a strange plume in an image. It was a volcanic eruption. Io was the most volcanically active body in the solar system, its interior kneaded and heated by the immense gravitational tug-of-war between Jupiter and the other moons. Europa appeared as a cracked, white billiard ball. Its surface was a global network of dark lines on a smooth, icy shell. The lack of significant craters suggested the surface was young and constantly renewing. Scientists began to whisper the thrilling possibility: a subsurface global ocean of liquid water, kept warm by tidal heating, could exist beneath that ice. The Great Red Spot was revealed in swirling, stormy detail. A hurricane twice the size of Earth, centuries old, a mystery of persistent atmospheric dynamics. Voyager transformed Jupiter from a distant, banded ball into a dynamic, complex system, a mini-solar system of interacting worlds where tidal forces cooked moons, radiation belts roared, and a storm larger than our planet raged endlessly. And this was just the first stop. The Voyagers were headed for Saturn, where an even more ethereal and mysterious giant awaited. Voyager 1's encounter with Saturn in November 1980 was a moment of pure celestial revelation. If Jupiter was the mighty king, Saturn was the ethereal queen, a world of impossible delicacy and sublime beauty. The rings, which from Earth appeared as a simple, flat structure, were now seen in staggering complexity. Voyager's cameras revealed thousands of individual ringlets, like the grooves on a cosmic phonograph record. There were dark gaps, braided rings, and mysterious, Radial spoke-like features that seemed to defy orbital mechanics. The rings were not solid. They were a vast, dynamic swarm of ice particles, ranging from dust grains to house-sized boulders, all orbiting in pristine, gravitational harmony. But Saturn itself held secrets. Its atmosphere, though less violently stormy than Jupiter's, displayed subtle bands and a mysterious, hexagon-shaped jet stream at its north pole, a perfect geometric storm six-sided in shape, each side longer than the diameter of Earth. How such a precise form could arise in a turbulent gas atmosphere remains one of planetary science's great puzzles. The real surprises, however, awaited among Saturn's moons. Titan, known for decades to have an atmosphere, was revealed to be shrouded in an impenetrable orange hydrocarbon haze. Voyager's instruments could not see the surface, but they detected a thick atmosphere of nitrogen and methane, with surface pressure 1.5 times that of Earth. It was the only moon known to have a substantial atmosphere, a world where chemistry reminiscent of early Earth might be unfolding in the deep freeze. Titan became an instant priority for future exploration. Other moons were equally astonishing. Mimas revealed a crater so large it looked like the Death Star from Star Wars. Iapetus presented a cosmic yin-yang, one hemisphere as dark as coal, the other as bright as snow. Enceladus, a small, bright moon, showed strangely young and smooth terrain, hinting at past geological activity. Voyager 2, following its twin, conducted its own Saturn flyby in August 1981, adding more detail before it embarked on its lonely journey to Uranus and Neptune. The Voyager missions had done more than send back postcards. They had fundamentally reclassified the giants. These were not merely larger versions of Earth. They were fluid worlds with no solid surface to stand on. Their surface was just the top of an ever-thickening atmosphere that merged seamlessly into a deep, hot interior of metallic hydrogen in Jupiter and Saturn, or superionic water in Uranus and Neptune. They were planetary systems in their own right, with collections of moons that rivaled the diversity of the inner solar system. But the Voyagers were flybys, brief, blazing passages. To truly understand a giant and its court, you must stay. You must orbit. The next great chapter in Jovian exploration began with Galileo, not the astronomer, but the NASA spacecraft named in his honor. Launched in 1989, the Galileo spacecraft arrived at Jupiter in 1995. Its mission was revolutionary. It deployed a probe that plunged directly into Jupiter's atmosphere on December 7, 1995. The Galileo probe, protected by a heat shield, dove into the Jovian clouds at over 100,000 miles per hour. For 58 minutes as it descended, it transmitted data on the composition, temperature, pressure, and winds of the giant's upper atmosphere. It found less water than expected, more noble gases, and winds that howled at over 400 miles per hour, even in the deep atmosphere. The probe was eventually crushed, melted, and vaporized, but it had given us our first and only direct taste of a giant planet's interior. The Galileo orbiter, meanwhile, spent 8 years studying the Jovian system. It witnessed a comet, Shoemaker-Levy 9, slam into Jupiter in 1994, a cosmic event that would have been catastrophic on Earth, but on Jupiter appeared as fleeting dark scars in the clouds. It conducted repeated, close flybys of the Galilean moons, transforming them from points of light into full-fledged geological worlds. It found strong evidence for a subsurface ocean on Europa, complete with possible chaos terrain, where icebergs might have rotated in slush. It confirmed the intense volcanic activity on Io, mapping hundreds of calderas. It revealed the complex, cratered ancient surfaces of Callisto and Ganymede, the latter showing signs of past tectonic activity. Galileo's mission ended in 2003 with a deliberate plunge into Jupiter's atmosphere, ensuring it wouldn't contaminate a potentially life-harboring moon like Europa. It left behind a legacy of data that would keep scientists busy for decades. For Saturn, the orbital explorer was Cassini-Huygens. Launched in 1997, Cassini spacecraft, with the European Huygens probe attached, entered Saturn orbit in 2004. Its mission was one of the most ambitious and successful in the history of space exploration. For 13 years, Cassini orbited Saturn, executing delicate maneuvers through the ring plane, skimming the cloud tops, and conducting over 100 close flybys of its moons. Its first historic act was to release the Huygens probe toward Titan. In January 2005, Huygens descended through Titan's opaque haze, its cameras finally revealing the surface no one had ever seen. It sent back images of a bizarre, yet hauntingly familiar landscape, river channels and shorelines carved by liquid methane, not water. It showed a dark, pebble-strewn plain where it came to rest. Titan was a frozen mirror of Earth, with a full hydrological cycle, but with methane as the working fluid at minus 180 degrees Celsius. Cassini itself went on to make discovery after discovery. It found towering geysers of water ice erupting from the south pole of the small moon Enceladus. This was not past geology. This was ongoing activity. Analysis of the plumes revealed they contained water vapor, organic molecules, and salts, strong evidence for a warm, salty, subsurface ocean in contact with the rocky core, making Enceladus a prime candidate in the search for life beyond Earth. Cassini meticulously mapped Saturn's rings, witnessing the gravitational birth of new moons, studying propeller-shaped features created by tiny moonlets, and observing the rings' changing appearance with Saturn's seasons. It watched giant, continent-sized storms erupt in Saturn's northern hemisphere. It dove between the planet and its innermost ring in its final, daring grand finale, orbits in 2017, sampling the atmosphere directly before its controlled plunge into the planet, ending its mission in a blaze of scientific glory. The age of the giants, once a realm of silent mystery, was now a documented epic of dynamic weather, ocean worlds, ice volcanoes, and complex ring physics. We had learned that the most likely places to find life in our solar system might not be on rocky planets, but in the subsurface oceans of the moons of gas giants. The revolution was complete. From points of light to fuzzy disks to sovereign realms of breathtaking complexity. The legacy of the giant planet revolution extends far beyond stunning images and rewritten textbooks. It has fundamentally altered our understanding of where we might find life, how planetary systems form and evolve, and what our own place in the cosmos might be. As we conclude this chapter on the kings and queens of the outer solar system, we look not just back at what we've learned, but forward to the mysteries that still call from the deep. The most profound shift in thinking concerns habitability. For centuries, the habitable zone was a simple concept, the Goldilocks region around a star where liquid water could exist on a planet's surface. Earth sat perfectly within our sun's zone. Mars, at its outer edge, was a maybe. Venus, inside it, was a tragic greenhouse. But the moons of Jupiter and Saturn have taught us that liquid water, and therefore the potential for life, does not require stellar warmth. It can be generated internally by tidal heating. The gravitational push and pull of a giant planet on its moons creates immense internal friction. This is the engine that drives the volcanoes of Io and keeps the subsurface oceans of Europa and Ganymede liquid. At Saturn, the same forces power the geysers of Enceladus and likely maintain a subsurface sea within Titan. Suddenly, the real estate for potential life in our solar system expanded exponentially. A star's habitable zone is just one neighborhood. The habitable moons around gas giants constitute an entirely new, and perhaps more common, galactic suburb. Our search for life is no longer focused solely on Earth-like planets. We must now consider water worlds hidden under ice, where chemosynthesis, not photosynthesis, might fuel entire ecosystems in perpetual darkness. The giants have also served as cosmic historians. Their compositions are thought to be largely unchanged since the formation of the solar system 4.6 billion years ago. By studying the ratios of hydrogen, helium, and heavier elements in their atmospheres, we can infer conditions in the primordial solar nebula. The complex chemistry in their atmospheres, the formation of clouds of ammonia and ammonium hydrosulfide, the hydrocarbons on Titan, are natural laboratories for prebiotic chemistry, showing us the steps that might lead to the building blocks of life under a wide range of conditions. Moreover, the ring systems, particularly Saturn's, are dynamic museums of orbital mechanics. They are natural experiments in how disks of material, be it gas and dust around a young star, or ice and rock around a planet, coalesce, spread, and interact. Studying the waves, gaps, and moonlets in Saturn's rings helps us understand the early stages of planet formation on a grand, stellar scale. The recent discovery that Saturn is losing its rings at a worst-case scenario rate, draining into the planet as icy rain, tells us these magnificent structures are not permanent. They are ephemeral cosmic wonders, and we are fortunate to live in the brief epoch where Saturn wears its crown. Yet, for all we have learned, the giants guard deep and tantalizing mysteries. What lies at the core of Jupiter? Data suggests a fuzzy, diluted core, perhaps the remains of a massive early planetesimal that triggered its runaway growth. What is the true depth of the Great Red Spot, and why has it persisted for centuries, while storms on Earth last days? What is the exact chemistry of Enceladus's ocean, and does it contain the right ingredients and energy sources to support microbial life? What strange cryovolcanic landscapes lie hidden under Titan's haze? And could there be life forms using liquid methane as a solvent? These questions drive the next generation of missions. NASA's Europa Clipper, set to launch in the coming years, will conduct dozens of close flybys of Europa, using ice-penetrating radar to map its subsurface ocean and spectrometers to analyze the composition of surface material potentially vented from below. ESA's JUICE, Jupiter Icy Moons Explorer, mission is en route to focus on Ganymede, Callisto, and Europa, seeking to understand these worlds as a system of potentially habitable environments for Saturn. Concepts for a Titan drone or a balloon, like the proposed Dragonfly mission, promise to explore its dunes and methane lakes directly. An Enceladus orbiter and lander remains a holy grail for astrobiologists, hoping to fly through its plumes and analyze them for the chemical signatures of life. As you listen now, in the quiet of your own space, let the scale of this revolution settle upon you. Just over 4 centuries ago, Jupiter and Saturn were wandering lights. Today we know them as vast, complex kingdoms, with families of active, ocean-bearing moons. We have sent robotic emissaries into their atmospheres and orbits. We have found that the most Earth-like body in the solar system is not a planet, but moon Titan, and that the most likely place to find a second genesis of life is under the ice of a small, bright moon, Enceladus or Europa. This knowledge transforms the night sky from a static backdrop into a dynamic map of ongoing discovery. When you see Jupiter as a bright beacon, you are not just seeing a planet. You are seeing a miniature solar system, a gravitational anchor for worlds with hidden oceans. You are seeing a guardian, whose massive gravity likely shielded the inner solar system from cometary bombardment in its youth, possibly aiding the development of life on Earth. When you see Saturn, you are seeing a celestial clockwork of unimaginable delicacy, a temporary masterpiece of ice and gravity. The story of the giants is a story of human curiosity scaling the impossible. We built lenses, then radios, then rockets, then robots, to cross billions of miles and decode the secrets of these distant realms. And in doing so, we didn't just learn about them. We learned about ourselves, about our capacity to question, to explore, and to continually rewrite the narrative of our home in the cosmos. So tonight, as you drift toward sleep, picture not emptiness between the stars, but a bustling, dynamic, and wet outer solar system. Picture the silent, dark oceans under Europa's ice, waiting. Picture the methane rain falling slowly on Titan's dunes. Picture the eternal storm of the Great Red Spot and the silent, glittering ballet of Saturn's rings. You are part of the first generation in history to hold these pictures in your mind, to know these places is real. Let that knowledge be a lullaby of connection. You are connected by curiosity and shared discovery to these far-flung worlds. Their stories are now part of our human story. And as you sleep, the giants continue their slow, majestic dance in the outer dark, keeping secrets we have only begun to guess. Our story begins not with a search, but with a routine survey. It is the night of March 13th, 1781, in the Garden of 19, New King Street, Bath, England. William Herschel, a German-born musician turned obsessive amateur astronomer, is scanning the sky with a magnificent hand-built telescope of his own design. Herschel is not looking for planets. He is engaged in a systematic review of the heavens, cataloging double stars. On this night, in the constellation of Taurus, he notes a curious object. It is not a point of light like a star, but a small, fuzzy disk. He initially records it as a nebulous star, or perhaps a comet. Herschel's comet did not behave like a comet. It moved too slowly, and its path was nearly circular, not the elongated ellipse typical of comets. As other astronomers across Europe tracked it, the truth became inescapable. Herschel had discovered a new primary planet, the first since antiquity. The solar system, stable and known for millennia, had just grown. King George III granted Herschel a pension, and the astronomer, in loyal thanks, named the new world Georgium Sidus, George's star. International astronomers, favoring mythological tradition, eventually settled on Uranus, the ancient Greek personification of the sky, father of Saturn and grandfather of Jupiter. The discovery of Uranus was a monumental, accidental triumph. It doubled the known radius of the planetary system at a stroke. It proved that the cosmos still held major, undiscovered worlds. Herschel became an instant celebrity, a symbol of the Enlightenment's power, a diligent amateur, armed with superior technology and method, could rewrite the map of the heavens. But Uranus, this new king of the distant frontier, soon began to behave badly. Astronomers, using Newton's laws of motion and gravitation, calculated precise tables predicting its future orbit. Yet, as decades passed and more observations piled up, Uranus stubbornly drifted from its predicted path. By the 1840s, the discrepancy was undeniable. The planet was being pulled off course. There were two possibilities, both deeply unsettling. Either Newton's law of universal gravitation, the bedrock of celestial mechanics, was wrong at such great distances from the sun, or there was another unseen mass, an eighth planet, tugging on Uranus with its gravity. The scientific community was divided. Many found the idea of a flaw in Newton's laws unthinkable. Others saw the mysterious tug as a thrilling challenge. The hunt for the phantom planet became the greatest scientific puzzle of the age, a test of human reason itself. Two brilliant, young mathematicians took up the challenge independently, on opposite sides of the English Channel. In England, John Couch Adams, a quiet, prodigious Cambridge graduate, began the calculations in 1843. In France, Urbain Le Verrier, a fiercely determined and meticulous astronomer at the Paris Observatory, started his work in 1845. Their task was Herculean: to work backwards from the observed irregularities in Uranus's motion, to calculate the mass, orbit, and current position of the unseen body causing them. They had to solve a gravitational inverse problem with only one data point: Uranus's errant path. Adams completed his first prediction in September 1845. He sent his results to James Shallis, director of the Cambridge Observatory, and to Sir George Airy, the Astronomer Royal at Greenwich. Airy, cautious and somewhat pedantic man, was skeptical. He requested more details. Adams, shy and perhaps overly deferential, did not aggressively follow up. His prediction languished. Le Verrier, unaware of Adams's work, published his own detailed calculations in June 1846. He was met with similar inertia from French astronomers. Undeterred, Le Verrier took a bold step. On September 18, 1846, he mailed his final prediction, complete with a precise position in the sky, to Johann Gottfried Galle at the Berlin Observatory. Le Verrier's cover letter was a masterpiece of confident deduction. Direct your telescope to a point on the ecliptic in the constellation of Aquarius, and you will find within a degree of that place a new planet, looking like a star of about the 9th magnitude. On the night of September 23, 1846, Galle received the letter. That very evening, with a clear sky overhead, he pointed the Berlin refractor to the coordinates Le Verrier had specified. His assistant, Heinrich d'Arrest, suggested they use a newly drawn star chart of that region to check for any object that wasn't supposed to be there. Within an hour of starting their search, just 52 minutes of arcade from Le Verrier's predicted position, they found a star that was not on the chart. They watched it for the next 24 hours. It moved. They had found the 8th planet. Le Verrier had been off by less than 1 degree. The news electrified the world. A planet had been discovered at the tip of a pen. It was a stunning validation of Newtonian mechanics and a testament to the power of human intellect. The new planet was soon named Neptune, after the Roman god of the sea. A fierce and somewhat unseemly priority dispute erupted between England and France over who deserved credit, Adams or Le Verrier. Today, history rightly credits them both. They had, independently and nearly simultaneously, solved one of the greatest predictive problems in science. The discovery of Neptune was not a lucky accident. It was a deliberate, calculated capture. It marked the moment astronomy matured from a science of observation to a science of prediction. But the story of mathematical triumph and of Neptune's own gravitational influence was not over. It would, in time, lead to another prediction, another search, and a far more controversial discovery that would shake our very definition of a planet. The discovery of Neptune seemed to be the final, triumphant proof of a complete and predictable solar system. Newton's laws reigned supreme from Mercury's swift orbit to Neptune's glacial one. Astronomers turned their refined mathematics and increasingly powerful telescopes toward the now 8 planets, confident that the major architecture of our celestial neighborhood was fully mapped. But the universe, it seems, enjoys confounding confidence. Even after Neptune's discovery, tiny, unexplained irregularities remained in the orbits of both Uranus and Neptune themselves. The gravitational pull of the known planets could not fully account for their precise motions. The ghost of an unseen perturber still lingered at the edge of perception. By the late 19th and early 20th centuries, the idea of a Planet X beyond Neptune took hold in the astronomical imagination. The most famous pursuer of this phantom was Percival Lowell, the same wealthy Bostonian who championed the canals of Mars. Lowell was convinced that a large, distant planet was causing the lingering orbital discrepancies. He established a dedicated search program at his Lowell Observatory in Flagstaff, Arizona, and spent the last decade of his life, until his death in 1916, calculating positions and scanning photographic plates for the elusive world. Lowell's calculations were flawed, based on erroneous assumptions about Neptune's mass, but the search continued after his death. The task fell to a young, meticulous Kansan named Clyde Tombaugh. Hired in 1929 as an observatory assistant, Tombaugh's job was to systematically image the same sways of the sky, nights apart, using a specially built blink comparator. This device allowed him to rapidly switch between 2 photographic plates of the same star field. Stars and galaxies would remain fixed. Any object that had moved relative to the background, an asteroid, comet, or distant planet, would appear to jump back and forth. It was tedious, eye-straining work, examining millions of pinpricks of light. Then, on February 18, 1930, after nearly a year of searching, Tombaugh was comparing plates taken in late January. In the constellation of Gemini, a faint, 15th magnitude object jumped. He checked a third plate. It had moved again, and in the right direction for a trans-Neptunian object. After weeks of confirmatory observations, the Lowell Observatory announced the discovery of the 9th planet on March 13, 1930, the anniversary of Herschel's discovery of Uranus and near Lowell's own birthday. The world celebrated. The new planet was named Pluto, after the Roman god of the underworld, a fittingly dark and cold ruler for such a distant realm. Initially, Pluto was thought to be the massive Planet X Lowell had sought, but problems arose almost immediately. Pluto was far too faint. Even early estimates suggested it was very small, likely smaller than Earth. Its mass was simply insufficient to cause the gravitational perturbations Lowell had tried to explain. As better measurements came in, Pluto shrank further. By the 1970s, it was clear Pluto was a tiny, icy world, smaller even than our moon. It could not be Planet X. The slight orbital anomalies of Uranus and Neptune, it turned out, were due to overestimations of Neptune's mass in early observations. Once Neptune's mass was correctly measured by the Voyager 2 flyby in 1989, the need for a Planet X to explain the outer planet's orbits vanished. Pluto's discovery was, in a sense, happy accident, a diligent search finding a real, fascinating object, but not the one it was looking for. Yet, Pluto's strange nature made it a compelling mystery in its own right. Its orbit was highly elliptical and tilted 17 degrees out of the plane of the other planets. For part of its 248-year journey, it comes closer to the Sun than Neptune does, as it did from 1979 to 1999. It was an oddball, an outlier. What was it doing out there? The answer began to emerge in the 1990s, not from a single discovery, but from a growing trickle, then a flood. With the advent of large, sensitive digital CCD cameras, astronomers could systematically survey the sky beyond Neptune. In 1992, astronomers David Jewett and Jane Liu discovered 1992 QB1, a small, icy body orbiting in a region we now call the Kuiper Belt, named for astronomer Gerard Kuiper, who had hypothesized a disk of icy debris in 1951. This was the first confirmed member of a vast, new population. The dam had broken. Dozens, then hundreds, then thousands of Kuiper Belt objects, KBOs, were catalogued. Pluto was no longer a lonely oddball at the edge of nothing. It was the largest known member, at the time, of a vast swarm. It was a Kuiper Belt object. This realization fundamentally changed its context. We hadn't found the ninth planet. We had found the first of a new class of solar system bodies. The crisis of definition came to a head with the discovery of Eris in 2005 by a team led by Mike Brown at Caltech. Initial observations suggested Eris was more massive than Pluto. If Pluto was a planet, then Eris certainly had to be one too. And what about other large KBOs like Makemake, Haumea, and later Sedna? Were we about to have 10, 20, 50 planets? The astronomical community faced a taxonomic emergency. The International Astronomical Union (IU), the governing body for such definitions, convened in Prague in 2006. After much debate, they voted on a new, three-part definition of a planet. It orbits the Sun. It has sufficient mass for its self-gravity to overcome rigid body forces, so that it assumes a hydrostatic equilibrium, nearly round shape. It has cleared the neighborhood around its orbit. Pluto and Eris satisfied the first two conditions, but failed the third. Their orbital zones are crowded with other KBOs. They were reclassified as dwarf planets, a new category for round objects that are not satellites and have not cleared their orbits. The public reaction was one of surprising emotional outrage. People felt a sense of loss. "Pluto got demoted," was the popular cry. But from a scientific perspective, nothing was demoted. Pluto was promoted. It went from being a misfit planet to being the prototype of the most populous class of major world in the solar system, the large Kuiper Belt object. Its context gave it deeper meaning. It was no longer the end of the line. It was the gateway to an immense, unexplored third zone of the solar system. The mathematical quest that began with Uranus's wobble had led, through Neptune and the flawed search for Planet X, to the discovery of Pluto, and ultimately to the revelation of an entire new frontier. The pen and the telescope, working in tandem, had once again redrawn the map, not by adding a single dot at the edge, but by revealing a whole new continent. The story of mathematical discovery in the outer solar system does not end with the redefinition. It enters a new, more profound phase. The shift from predicting single, massive worlds to mapping the gravitational architecture of the void itself. The Kuiper Belt is not a random scattering of ice. It is a structured forensic record, and its patterns whisper secrets about the solar system's violent youth. When astronomers began plotting the orbits of the thousands of KBOs they discovered, they noticed something strange. While many orbit in a relatively flat disk akin to the planets, a significant population, including the highly distant object Sedna, have orbits that are extremely elongated and tilted. Their closest approach to the Sun is far beyond Neptune, yet they swing out to breathtaking distances. Sedna's orbit takes it over 900 times farther from the Sun than Earth at its most distant point. These orbits cannot be easily explained by the gravitational influence of the known planets alone. This is where mathematics again takes the lead, pointing not to a single planet X, but to a historical gravitational drama. The leading theory to explain these detached, extreme orbits is the Planet 9 hypothesis, proposed by Caltech's Konstantin Batygin and Mike Brown, the Pluto killer, in 2016. It suggests that the peculiar clustering of the orbits of these distant objects could be best explained by the gentle, persistent tug of a still undiscovered planet, perhaps 5 to 10 times the mass of Earth, orbiting hundreds of times farther out than Earth on a slow, millennia-long path. This would not be the massive gas giant envisioned by Lowell, but a smaller, icy super-Earth or mini-Neptune, a frozen relic from the dawn of our system. The hunt for this hypothetical Planet 9 is today's great mathematical celestial quest. It is conducted not by blinking comparators, but by running sophisticated orbital simulations on supercomputers and then directing the world's most powerful survey telescopes, like Subaru in Hawaii, to scan the most likely slivers of the immense sky where it could be hiding. It is a needle in a haystack search on a galactic scale, guided entirely by the subtle gravitational fingerprints left on the orbits of tiny, distant ice fragments. Whether it exists or not, the very hypothesis demonstrates how we now use mathematics, not just to find a planet, but to reconstruct the history of the solar system. The Kuiper Belt structure tells another story, one of planetary migration. The Nice model, named for the city in France where it was developed, uses complex gravitational simulations to propose that the giant planets did not form in their current positions. In the early solar system, Jupiter, Saturn, Uranus, and Neptune were packed closer together, nestled within a vast, dense disk of icy planetesimals, the primordial Kuiper Belt. Gravitational interactions caused the giants to slowly migrate. Jupiter moved slightly inward, while Saturn, Uranus, and Neptune moved outward. This migration scattered the icy disk, flinging most of it inward to bombard the inner planets, the late heavy bombardment, and outward to form the scattered disk we see today. Neptune's outward march, in particular, shepherded and sculpted the Kuiper Belt. The orbits we see now are frozen echoes of that ancient dance. Thus, the Kuiper Belt is more than a collection of icy rocks. It is the solar system's archaeological site. Each peculiar orbit is an artifact, a clue to the gravitational forces that shaped our cosmic neighborhood billions of years ago. By reading these clues with mathematics, we are writing the biography of the solar system's first 100 million years. This journey, from Uranus's wobble to Planet Nine's hypothetical sway, represents the ultimate evolution of discovery. We have moved from accident Uranus to calculation Neptune, from miscalculation, the search for Planet X, to serendipitous discovery Pluto, from classification Pluto as planet to contextualization Pluto as Kuiper Belt king, from finding objects to decoding history, from orbital patterns. The outer dark is no longer an empty margin on the map. It is a dynamic, structured, and historically rich frontier. And we know this not because we've visited it all. We've only sent one spacecraft, New Horizons, on a brief flyby, but because we have learned to see with the mind's eye. We see the gravitational footprints in the void. As you listen now, let this intellectual triumph be a source of quiet awe. The same human mind that worries about daily tasks is also capable of perceiving the ghostly tug of an unseen world a billion miles away. By studying the minute deviation in the path of another world a billion miles from that, we inhabit a universe that is rational, lawful, and therefore knowable. The fact that we can predict Neptune from Uranus, or postulate Planet 9 from Sedna, is a profound testament to this cosmic order. So tonight, when you think of the solar system, picture not just the familiar planets, but the invisible scaffolding of gravity that connects them. Picture the distant, dark disk of the Kuiper Belt, teeming with frozen worlds, its structure a memory of planetary giants on the move. Picture the possibility of a still-hidden world, so far out that the sun is just a particularly bright star, its existence inferred only by the delicate dance of tiny specks of ice even farther away. We are part of species that maps not just what is seen, but what must be. We fill in the blanks of the cosmos with logic, and time and again, the cosmos confirms our logic. This is the true victory of mathematics, not just in finding planets, but in revealing a universe that is, at its heart, comprehensible. Let that comprehensibility lull you. In a world of surface chaos, the deep laws are constant and calm. The same gravity that holds you to your bed tonight is orchestrating a ballet on scales so vast they defy imagery. You are connected to that ballet by the faculty of your understanding. Now, release the calculations. Let the numbers fade. What remains is the beautiful, silent certainty that out there in the dark, the laws are holding, the orbits are turning, and the story is still being written. And we, with our curious minds, are reading it. We begin with the morning and evening star, Venus. For millennia, it was the most beautiful object in the sky after the sun and moon, a dazzling, serene beacon in the twilight. Its thick clouds, reflecting sunlight brilliantly, hid its surface completely. This veil was a perfect screen for projection. In the absence of data, imagination flourished. By the late 19th and early 20th centuries, as astronomy matured, a consensus view of Venus emerged. It was Earth's sister planet. Similar in size, mass, and residing closer to the Sun within the theoretical habitable zone, it was logical to assume it was a warmer version of Earth. The clouds were surely water vapor. The surface, therefore, must be a global, steaming tropical swamp, a primordial carboniferous jungle, teeming with exotic life, perhaps giant ferns and lumbering reptiles. It was a vision of Earth's past, a living museum of the Mesozoic era, wrapped in clouds. Prominent astronomers like Percival Lowell, again, speculated about a planet-wide ocean. The public devoured science fiction stories of Venusian jungles and alien civilizations. It was a hopeful, verdant dream. Mars, the red planet, inspired a different, more anxious fantasy. Its ruddy hue suggested deserts. Its polar ice caps grew and shrank with the seasons. Through earthbound telescopes, astronomers could make out vague, darkish patches that seemed to change shape and intensity with the Martian seasons. The most influential observation was made by Italian astronomer Giovanni Schiaparelli. During the favorable opposition of 1877, he mapped Mars and described linear features he called canali, Italian 4 channels, natural or otherwise. The translation to English as canals was a linguistic and imaginative catastrophe. Canals implied artificial construction. The idea was seized upon and evangelized by Percival Lowell, who, with boundless energy and personal wealth, built the Lowell Observatory in Flagstaff, Arizona, primarily to study Mars. Lowell produced elaborate maps showing a global network of hundreds of straight lines, intersecting at dark oases. He argued these were irrigation canals built by a dying, intelligent civilization to transport water from the melting polar caps to the arid equatorial cities. Mars, in Lowell's vision, was a planet of ancient engineers fighting a desperate battle against a drying world. It was a parable of ecological hubris and decline, a warning for Earth. Lowell's theories, though dismissed by many professional astronomers as optical illusion and wishful thinking, captured the public imagination with ferocious power. The concept of Martian canal builders permeated literature, from H.G. Wells's Invasive War of the Worlds, 1898, to Edgar Rice Burroughs's romantic Barsoom series. Mars became a cultural fixture, a symbol of intelligent life, but also of senescence and existential threat. These twin visions, the swampy, living Venus and the engineered, dying Mars, were not malicious fictions. They were extrapolations based on the best available, but utterly insufficient data. They were examples of the scientific method's vulnerability, the human tendency to fill data voids with reasonable, often self-reflective assumptions. We saw what we expected to see, what we feared, and what we hoped for. The first cracks in these fantasies appeared not with spacecraft, but with new ways of sensing from Earth. For Venus, the key was radio astronomy and radar. In the 1950s, radio telescopes detected microwave emissions coming from Venus. The intensity of these emissions suggested a scorching hot surface, hundreds of degrees Celsius, not a balmy swamp. This was confusing and controversial. Perhaps the radio waves were coming from a hot layer in the atmosphere, not the surface. The definitive blow to the jungle Venus came in 1962. NASA's Mariner 2 spacecraft, the first successful planetary flyby, sped past Venus. Its microwave radiometer confirmed the horrific truth. The surface temperature was at least 425 degrees Celsius, 800 degrees Fahrenheit, hot enough to melt lead and zinc. The clouds were not made of water vapor, but of sulfuric acid. Venus was not a sister. It was a twin from hell, a chilling example of a runaway greenhouse effect. The dream of a steamy paradise, vaporized in the face of data. Venus was a cautionary tale written in acid and heat. For Mars, the disillusionment was more gradual, but no less definitive. Early spectroscopic studies from Earth found almost no oxygen or water vapor in its thin atmosphere. The canals remained stubbornly elusive in photographs. They appeared only in visual sketches by observers under moments of perfect seeing. As telescope optics improved, the straight lines broke up into disconnected smudges and patches. The astronomical community grew increasingly skeptical. The death knell for Lowell's Mars was struck by a spacecraft. On July 14, 1965, Mariner 4 flew by the red planet and took 21 grainy, close-up photographs. The world waited, hoping for glimpses of canals, cities, or any sign of order. What they saw was a barren, cratered, moon-like landscape. No canals, no cities, no signs of water or life. The atmosphere was confirmed to be vanishingly thin, mostly carbon dioxide. Mars was not a dying civilization. It was a largely dead world. The public and scientific letdown was profound. The great Martian myth had been, as scientist Bruce Murray put it, murdered by a handful of digital bits. We had been utterly wrong, but being wrong was the prerequisite for starting to be right. The age of projection was over. The age of exploration was about to begin. The blunt force trauma of Mariner 4's images did not end our relationship with Mars. It transformed it. The romantic, engineered Mars was dead. In its place arose a new, more compelling mystery, a geological Mars. If there were no canals, what had carved the vast canyons, stacked the layered polar deposits, and built the largest volcanoes in the solar system? The quest shifted from searching for engineers to reading the planet's physical history written in its rocks. The Mariner 9 orbiter, arriving in 1971, revolutionized our understanding. A global dust storm was raging when it arrived, but as the storm cleared, Mariner 9's cameras revealed a world of staggering grandeur. It saw Valles Marineris, a canyon system so vast it would stretch from New York to Los Angeles, dwarfing the Grand Canyon. It photographed Olympus Mons, a shield volcano nearly 3 times the height of Mount Everest, with a footprint the size of Arizona. It captured winding, dried-up river valleys, clear evidence that liquid water had once flowed on the Martian surface. Mars was not a static, dead moon. It was a world with a complex, active past. It had atmosphere, volcanism, and most importantly, water. The question changed from "Is there life?" to "Was there ever life? And where did the water go?" This set the stage for the era of landers. Viking 1 and 2 touched down in 1976. Their mission was explicit: search for life. They conducted sophisticated biology experiments, mixing Martian soil with nutrients and looking for signs of metabolism. The results were ambiguous, frustrating, and ultimately interpreted as negative. The chemical reactions observed were likely due to exotic soil chemistry, not biology. The Viking landers painted a picture of a cold, dry, windswept desert under a pink sky, with soil more reactive and hostile than any on Earth. The hope for extant surface life dwindled to near zero. The subsequent decades were a march of robotic geologists. Pathfinder/Sojourner, 1997, proved the concept of mobile exploration. The Mars exploration rovers, Spirit and Opportunity, 2004, were triumphs of endurance, trundling across the landscape for years. Opportunity, in particular, found conclusive mineralogical proof of ancient, persistent liquid water, hematite blueberries, and sulfate salts that only form in wet conditions. Mars had not just had fleeting floods. It had had long-lived, potentially habitable environments. The Mars Reconnaissance Orbiter, 2006, with its high-resolution camera, began spotting recurring sloped lineae, dark, seasonal streaks on sun-facing slopes that hinted at possible, briny liquid water seeping to the surface in the modern era. The Curiosity rover, 2012, a car-sized laboratory, landed in Gale Crater, an ancient lakebed. It has since climbed a mountain, analyzing layers of sedimentary rock, finding complex organic molecules, and confirming that ancient Mars had the right chemistry, water, essential elements, and energy sources to support microbial life for perhaps millions of years. Today, Perseverance rover 2021 is actively collecting rock cores in Jezero crater, a former river delta, for eventual return to Earth, the first Mars sample return mission. Its companion, the Ingenuity helicopter, proved that powered flight is possible in Mars's thin atmosphere. We are no longer just observing Mars. We are conducting field geology on another world, piece by piece reconstructing its climate history from a time when it was a warmer, wetter, potentially life-bearing planet. Mars has been transformed from a canvas for our fears into a scientific puzzle of the highest order. It is a museum of planetary climate change, showing us how a world can lose its atmosphere and water. It is a potential tomb for ancient, simple life. And it is a proving ground for the technologies and techniques we will need to become an interplanetary species. Venus, meanwhile, followed a different, slower path to understanding. After the shock of its hellish surface conditions, it was largely abandoned for the more promising Mars. But few daring missions ventured back. The Soviet Venera program achieved what remains one of the most heroic feats in space exploration, landing on the surface of Venus. Venera 7, 1970, was the first to successfully transmit data from the surface, confirming the crushing pressure and infernal heat. Venera 9, 1975, sent back the first and only photographs from the Venusian surface, showing a rocky, desolate landscape under a diffuse, yellowish sky. Subsequent Venera landers analyzed the soil, finding basaltic rocks similar to Earth's ocean floors. The American Pioneer Venus Orbiter, 1978, and Magellan Orbiter, 1990, used radar to map the entire surface through the clouds. Magellan's maps revealed a world without plate tectonics as we know it, but with evidence of global resurfacing by vast volcanic floods in the relatively recent geological past. It showed coronae, crown-like circular structures, tesserae, highly deformed highlands, and few impact craters, indicating a geologically young surface. For decades, Venus was seen as a static dead end, a warning of greenhouse gone wild. But recently, a tantalizing new possibility has emerged. Data from the European Venus Express Orbiter, 2006 to 2014, and new analysis of old data suggest that Venus may have had a temperate, shallow ocean for up to 2 to 3 billion years of its early history, a duration comparable to the time life took to arise on Earth. Only later did a runaway greenhouse effect boil it away. Furthermore, the controversial detection of phosphine gas in Venus's clouds in 2020, a gas that on Earth is primarily produced by life or extreme industrial processes, has reignited the question, could simple, aerial microbial life exist in the temperate, upper cloud layers of Venus, floating in droplets of sulfuric acid? It is a long-shot hypothesis, but it has brought Venus back into the astrobiological conversation, from swamp to hellscape, and now to a possible ancient ocean and the speculative aerial biosphere. Venus's story is a roller coaster of scientific revision. It teaches us that planetary destinies are not fixed. They can diverge dramatically due to subtle differences in composition, distance from the sun, and perhaps sheer luck. The journeys to Mars and Venus have given us more than revised planetary profiles. They have delivered profound, and often humbling, lessons about our own world. These neighboring worlds, once our mirrors, have become our comparative planetology laboratories. By studying their extremes, we better understand the delicate, precious balance that makes Earth a living world. Mars teaches us about fragility. It shows us a planet that likely started with a thicker atmosphere and flowing water, a potentially habitable environment. But something went wrong. Mars is smaller than Earth, with about half the diameter and only 11% of the mass. This smaller size meant its internal dynamo, the churning of molten metal that generates a global magnetic field, faded early. Without this protective magnetic shield, the solar wind, relentless stream of charged particles from the sun, began to strip away Mars's atmosphere, molecule by molecule, over billions of years. As the atmospheric pressure dropped, surface water could no longer remain liquid. It either froze into the ground or was lost to space. The planet entered a deep freeze, its water now locked in polar ice caps and subsurface permafrost. Mars is a case study in atmospheric escape and climate collapse. It is a stark reminder that a planet's habitability is not a permanent state, but a condition that must be maintained. Our own magnetic field and substantial gravity are silent guardians we often forget to thank. Venus, on the other hand, teaches us about runaway processes. It is a vision of Earth's worst-case climate future. While the cause of its extreme greenhouse effect is still debated, possibly due to increased solar heating as the sun brightened over time, coupled with a lack of a water-based cycle to remove carbon from the atmosphere. The result is clear: a surface hot enough to melt lead, under an atmosphere of crushing pressure. Venus shows us that the carbon cycle, which on Earth regulates temperature by sequestering carbon in rocks and oceans, can break down. It is a warning of what can happen when positive feedback loops take over. Studying Venus's sulfuric acid clouds and superrotating winds helps us refine climate models for Earth. It forces us to ask, what tipping points exist in our own climate system that we must avoid? These lessons move us from myth to stewardship. We no longer look at Mars and see dying civilizations to pity or invade. We see a preserve of ancient planetary history that we must protect from contamination as we search for signs of past life. We no longer look at Venus as a hellish jungle to be avoided. We see a natural laboratory for atmospheric physics and a cautionary tale for our own planet's future. This shift in perspective is perhaps the greatest discovery of all. We have learned that our solar system is not a collection of isolated, static worlds, but a dynamic system of interlinked histories. The asteroid belt tells of a planet that failed to form. The gas giants' migrations shaped the fates of the inner planets. The water in Earth's oceans may have been delivered by comets and asteroids from the outer system. We are connected to Mars by the shared possibility of life, and to Venus by the shared danger of climate catastrophe. As you listen now, let this interconnectedness be a source of both humility and calm. You are living on the rare, lucky planet in this trio. You breathe an atmosphere forged by biology. You are protected by a magnetic field generated by a still active core. You live within a complex, self-regulating system that has maintained habitable conditions for billions of years. Knowing the fates of your neighbors makes your own world not smaller, but more precious, more unique, and more worthy of care. The age of projection is over. We no longer need to populate other worlds with our fantasies, because we are busy uncovering their truths, truths that are more astonishing, more varied, and more instructive than any fiction. The dry riverbeds of Mars and the volcanic plains of Venus are not disappointments. They are chapters in a grand, universal story of planetary evolution, of which Earth is another, ongoing chapter. So tonight, as you drift toward sleep, picture not the Mars of warlords or the Venus of monsters. Picture the real Mars, a cold, silent desert under a pale pink sky, where a robotic geologist, millions of miles away, switches into low-power mode for the night, its solar panels tilted toward a distant, setting sun. Picture the real Venus, a world of eternal twilight under thick, yellow clouds, where the very rocks glow with trapped heat, and any memory of an ocean is baked into the mineralogy of its highland rocks. These are not failures of imagination. They are triumphs of discovery. We have traded comforting myths for challenging, beautiful realities, and in doing so, we have grown up as a species. We have learned to see the universe not as a backdrop for our dramas, but as a place with its own independent story, a story we are privileged to be able to read, piece by painstaking piece. Let the steady, silent work of those distant robots be a metaphor for your own mind tonight. There is no need for dramatic stories or frantic thought. There is only the quiet, patient acquisition of truth, the gentle acceptance of reality as it is, not as we wish it to be. The rovers are at rest. The orbiters are silently tracking. The data is being gathered. All is proceeding according to the peaceful, predictable laws of physics. You can rest now on your own rare and beautiful world, cradled in the same physical laws that govern the silent desert of Mars and the glowing rocks of Venus. You are safe. You are part of the story, and the story continues at its own majestic, unhurried pace. Welcome to the final chapter of our journey. We have traveled from the mistaken lights of ancient skies to the calculated shadows of unseen worlds. We have walked the dead riverbeds of Mars and felt the crushing heat of Venus. We have witnessed the majestic courts of Jupiter and Saturn and peered into the icy frontier of the Kuiper Belt. Now we arrive not at an end, but at a vista. It is time to step back, to let the myriad discoveries of these past hours settle into a single, coherent picture. A picture not of a small, known family of worlds, but of a vast, dynamic, and deeply connected cosmic ecosystem. This is the new solar system, and understanding it is the key to a profound and lasting peace. Let us construct this new map together in your mind's eye. Start at the center with our sun, not just a light, but a gravitational anchor, a nuclear furnace whose gentle output of light and fierce output of a solar wind shapes the entire domain. Now, picture the inner, rocky realm. Mercury, a scorched, cratered world of extremes. Venus, a shrouded, volcanic pressure cooker, a warning etched in acid and heat. Earth, our blue-green marble, teeming with life, a fragile bubble of breathtaking complexity. Mars, the cold, rusty desert, holding the frozen memoirs of ancient rivers and seas. This is the realm of silicate and iron, of geology and lost climates. Surrounding this realm is the asteroid belt, not a shattered planet, but a construction yard that never finished, a countless swarm of rocky and metallic leftovers, the building blocks of worlds that never were. Now cross a great gulf. Enter the realm of the giants. First, Jupiter, the king, a striped, storm-racked sphere of hydrogen and helium, a magnetic behemoth with a family of moons that are worlds unto themselves. Volcanic Io, icy ocean Europa, giant Ganymede, ancient Callisto. Its gravity is a shepherd, a protector, a sculptor. Next, Saturn, the jewel, its rings a breathtakingly complex disk of ice, a celestial carousel. Its moons are wonders. Haze-shrouded Titan with its methane lakes, icy Enceladus with its subsurface ocean venting into space. Then the ice giants, Uranus and Neptune, pale blue-green, tilted worlds of water, ammonia, and methane ices, with their own dark rings and strange moons like retrograde Triton. They are the sentinels of the deep. But do not stop here, for beyond Neptune lies not emptiness, but the Kuiper Belt, a vast, donut-shaped swarm of icy bodies. Here, Pluto reigns not as a lone outcast, but as a dwarf planet prince among thousands, with its heart-shaped glacier and family of moons. Here reside Haumea, Makemake, Eris, and countless other frozen relics. And even farther, imagine the scattered disk, objects flung into wildly elongated orbits, and the spherical shell of the Oort cloud, a reservoir of trillions of icy bodies so distant that the sun is just a bright point, whose occasional members fall inward as long-period comets. This is the solar system, not 9 planets, but a nested, structured system of zones. The rocky inner zone, the asteroid belt, the construction zone, the giant planet zone with their satellite systems, the ice dwarf / Kuiper Belt zone, the scattered disk and Oort cloud, the primordial icy reservoir. This new map is not just bigger, it is alive with process. It is a system where gravity orchestrates a grand dance from the sun's heart to the Oort cloud's fringe. Impacts from asteroids and comets have delivered water and organic molecules to the inner worlds, possibly seeding the ingredients for life. The migration of giant planets and their youth shaped the fates of the smaller ones, scattering comets and asteroids. Tidal forces heat moons, creating subsurface oceans in places far from the sun's warmth. Solar wind and magnetic fields carve invisible bubbles and bow shocks in the interstellar medium. We are not living on a planet in isolation. We are living on a participant in a vast, slow-motion ballet of matter and energy that has been unfolding for 4.6 billion years. Every comet that graces our night sky is a visitor from system's outermost freezer. Every meteor shower is the dust of ancient asteroids. The water in your glass may contain hydrogen atoms that once drifted in the cold, dark cloud that gave birth to the sun. This perspective is the antidote to insignificance. You are not a tiny being on a lonely rock. You are a conscious expression of a hyperconnected, astronomically ancient system. Your planet is a node in a cosmic network of unbelievable scale and intricate history. As you absorb this, feel your sense of scale shift. The worries of the day, the confines of the room, the boundaries of your own skin. They are real, but they are not the whole story. The whole story encompasses the solar wind brushing past Voyager 1 in interstellar space, the icy geysers of Enceladus, the silent dunes of Titan, and the slow, eternal turn of the gas giants. You are connected to all of it by the simple fact of your existence within the system. So, as we prepare to go deeper into the night, carry this map with you. You're going to sleep not just in a bed, in a room, on a planet. You are going to sleep in the inner rocky zone of a magnificent stellar system. You are safe. You are home. And home is far vaster and more wonderful than we ever dreamed. With this new map of our cosmic home firmly in mind, we can now ask the most profound question this journey invites. What does this knowledge do to us? Beyond the facts and the images, how does living with the reality of the new solar system change our inner landscape? The answer lies in a series of gentle but powerful shifts in perception, each one a stepping stone to a deeper, more resilient peace. First, it installs a sense of cosmic time. The processes that shaped our system, the accretion of planets, the late heavy bombardment, the migration of giants, the slow freezing of Mars, the runaway heating of Venus, unfolded over billions of years. Human history, even the entirety of life on Earth, is a brief flicker on this timescale. Your own life, with its joys and worries, is a single, precious heartbeat in this immense, slow-breathing entity. This is not diminishing, it is liberating. The pressures of immediacy soften when viewed against the patient, gradual work of geology and orbital mechanics. The mountain that stresses you today is a temporary wrinkle on a planet that has seen continents form and oceans boil away. Your worries are real, but they are not eternal. The solar system teaches patience by its very existence. Second, it fosters a humility born of correction. Our story has been one of getting it wrong, over and over. We placed Earth at the center. We saw canals on Mars and jungles on Venus. We thought Pluto was the final planet. Each time, reality, patiently revealed through better tools and clearer thinking, corrected us. This is the essence of science, not a march of arrogant certainty, but a graceful dance of error and refinement. Embracing this teaches us to hold our own current views lightly, to be open to being delightfully wrong, to see correction not as failure, but as growth. In your own life, this translates to a lighter grip on fixed opinions, a quieter mind that can accept new information without threat. Third, it reveals resilience through interconnection. The solar system is not a collection of isolated marbles in a void. It is a web of gravitational and chemical relationships. Jupiter protects the inner planets. The moon stabilizes Earth's tilt. Comets from the Oort cloud may have delivered water. This interconnectedness is a form of cosmic resilience. The system maintains its structure through dynamic balance. For you, this is a metaphor for your own life. You are not an isolated self. You are a node in a web of relationships, biology, culture, and history. Your strength is not just in your individuality, but in your connections. Like a moon held in orbit, you are supported by a network of unseen forces: gravity, love, community, biology. Fourth, and perhaps most importantly for sleep, it replaces mystery with wonder. There is a profound difference. Mystery can breed anxiety, the fear of the unknown, the unsettling blank space. Wonder is the joy of the known unknown, the delighted engagement with something vast and beautiful that you can partly understand. The ancient night sky was a mystery, filled with gods and portents. Our modern night sky is a wonder. We know those points of light are worlds, and knowing what they are, a gas giant, an ice dwarf, a volcanic moon, only deepens their beauty. The fear is gone, the majesty remains. As you lie in the dark, you can replace the mystery of what's out there with the wonder of I know what's out there, and it is magnificent. This turns the darkness from something potentially threatening into a canvas for peaceful contemplation. Now, let's apply this directly to the ritual of sleep. Your journey tonight mirrors, in a small, beautiful way, the cosmic cycles we've explored. Your day is like the inner, rocky zone, active, heated by the sun of your consciousness, full of impacts and events. The act of closing your eyes and beginning to relax is like crossing the asteroid belt, a transition from the busy inner system to the quieter, more spacious realms beyond. The descent into deep, slow-wave sleep is your journey into the realm of the giants, a state of immense, slow, powerful restorative processes. where the day's mental debris is cleared and your body is repaired. And your REM sleep, your dreaming, is your Kuiper belt, a creative, icy, loosely bound realm where memories and emotions recombine in strange, new, and distant formations. You are not just falling asleep. You are embarking on a mini grand tour of your own inner solar system, and you do this every night. Trust the itinerary. The gravity of your biology will pull you through the cycles. The solar wind of your breath will flow steadily. The orbits of your thoughts will gradually widen and slow. You are a universe unto yourself, operating under the same principles of cycles, energy, and restoration as the great universe outside. There is profound comfort in this symmetry. The macrocosm and the microcosm reflect each other. So, as you feel sleep drawing nearer, consciously align yourself with these greater rhythms. You are not fighting to sleep. You are synchronizing with a rhythm that governs moons, planets, and stars. Your surrender to sleep is not a defeat. It is an act of cosmic alignment. We have reached the final threshold, the edge of waking, the shore of sleep. The story is told. The map is drawn. The connections are made. Now it is time for the words, the concepts, the very voice you hear, to dissolve. They have done their work. They have built a bridge of understanding between your waking mind and the silent, spacious reality of the cosmos. Now, you must cross that bridge alone, leaving the bridge itself behind. So, let us begin the gentle work of dissolution. First, release the scale. Let go of the billions of years, the millions of miles. They are true, but they are not needed here, in the dark of your room. Feel instead the immediate scale, the soft pressure of the pillow, the weight of the blanket, the cool air on your face. The universe is vast, but your experience of it right now is intimate, close, and quiet. Now release the names. Let Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, and all their moons fade. They are out there, doing what they do, whether you name them or not. Their dance does not require your recognition. They are free, and so are you, free from the need to catalog, to know, to hold in mind. Next, release the stories, the discoveries, the conflicts, the triumphs and errors of Herschel, Galileo, Leverrier, Tombaugh. Let them go. They are history. Their work is done, and it has given you this moment of peace. You do not need to carry their struggles. They can rest, and so can you. Then release the lessons, the humility, the interconnectedness, the wonder. These are not ideas to clutch. They are impressions to absorb and then release, like a soil-absorbing rain. Let them seep into the background of your being, where they will work without your conscious effort. What remains when all this is let go? Sensation, the rise and fall of your own breath, the faint, rhythmic pulse in your ears or your neck, the slight, pleasant heaviness in your limbs. Darkness, not an empty darkness, but a full darkness, a darkness that contains everything we have spoken of, but holds it silently, without form, like a seed contains a forest. It is the darkness of the womb of space itself, nurturing, holding, waiting. Sound, perhaps the gentle ambient tone that has been threading through this story. Hear it not as a sound, but as a vibration, a standing wave in the room, a harmonic of the earth's own quiet hum, a lullaby sung by the physics of the universe itself. This is your destination, not a place of thought, but a place of being. You are a living planet, orbiting the star of your own consciousness, now preparing to turn your face away from that light for a while, to journey into your own inner night. As you cross over, imagine that you are not falling asleep, but attending. You are attending the great, silent council of the solar system. You are taking your place, not as a thinker, but as a participant. You are the representative from Earth. You bring with you nothing but your awareness and your breath, and that is enough. The council is not a meeting of words. It is a meeting of states. The fiery state of the sun, the solid, watery state of Earth, the gaseous, stormy state of Jupiter, the icy, serene state of Pluto. And now, you bring the resting state of the human mind. Add it to the chorus. Let your quiet mind resonate with the deep, slow frequencies of orbital harmony. There's no more to do, no more to understand. The voyage is complete. You have traveled from misunderstanding to clarity, from a small sky to a vast system, from anxiety to belonging. Now, let the voice that guides you become softer, farther away, like a friend waving from the dock as your ship gently drifts from shore. The ship is your own body, your own mind. It knows the way. The currents of sleep are pulling you now, and they are the same currents that move the planets in their paths, currents of natural law, of perfect, effortless balance. I will be quiet soon. The sounds will fade. The last thing you will hear is the soft, resonant tone, and then it too will vanish into the silence from which it came. You are ready. You are more than ready. You are a child of this spectacular, interconnected system, and you are coming home to rest within it. Good night.